Welcome, Mechanics of Materials students. In this short lecture, we're going to be putting together what we've learned about strain and about stress in previous lectures and looking at what happens when we evaluate stress and strain together in a given material. This lecture is going to mostly be qualitative, so we're going to examine general characteristics of how materials behave when we apply stress. What kind of strain do we see, and what kind of stress would we expect if we require a material to undergo displacement that would result in a certain strain. We'll look at elasticity, plasticity, time-dependent change, and then kind of center ourselves in the arena of those types of material behaviors that we'll be generally working in as engineers. So just to recap, elastic material responses, and then elastic material responses is one type of material response we'll go over. In that, we look at our strain tensor, which we're seeing right here, our EIJ. We say that if a material is behaving elastically, the whole strain tensor is going to be a function of applied stress at a given temperature. That's what the T is there. And stress is going to be a function of strain at a given temperature. So a way to say that with words is stress and strain have a one-to-one relationship at a given point in a material at a given temperature. So if we know the stress state at that point, so that means our normal stresses, our shear stresses, and we measure the temperature at a given point in a material, and we know that it's behaving elastically, we should be able to calculate from the elastic properties of that material its entire state of strain, and vice versa. Another fabulous property of elastic material behavior is that it is what's called path independent. So it doesn't matter how quickly you apply stress. It doesn't matter how much time you take, which is another way of saying how quickly. It doesn't matter if you apply a little bit of stress now and then 5 minutes later apply more and then take some of it away. Your ending state of strain will only depend on what your ending stress is. Doesn't matter how you got there. So those of you who have taken thermodynamics may have heard of state variables versus process variables. Elastic material behavior can be thought of as a state variable. It only matters where you are in terms of how much strain is present at a given temperature. You'll know the stress. If you know what the state of stress is, it doesn't matter what it was yesterday. Didn't matter how quickly you applied it. You could measure or calculate the resultant strain at that point. Okay. This is not true of any kind of non-elastic behavior. Okay, so what's non-elastic? Time-dependent behavior. There's some materials whose entire array of mechanical properties change with time and or with temperature, or a combination of time and temperature. This is usually due to certain chemical reactions and chemical processes occurring within the material that are both time and temperature dependent. Two typical ones that you might see in practice are curing adhesives and curing concrete. Those of you who will use metals or specify different types of thermomechanical processing for metals will find that different types of heat treatment result in aging material behavior, which means time-dependent material behavior. Precipitation hardening of aluminum being a noteworthy one that you might encounter with aerospace materials. Okay, so that's material aging. Material properties like yield stress, possibly even elastic modulus, those are all material properties we'll discuss. Those can change with time if a material's aging. For the most part, nothing that we discuss in this class is going to concern itself with aging materials. If so, you'll be told something like on day one, you know that modulus, yield strength, etc. is X, and it follows some time-dependent aging. How would you expect it to behave 6 months into service? But you would have to know how the material properties change with time. So for the most part, you'll assume that you're evaluating something at a given time, and so changes with time aren't important. Okay, how about rate dependence? A lot of times materials, for those of you in civil engineering, you're going to encounter what's known as dead loading, dead loads where the load is constant, so you can assume that the stresses aren't changing with time. But we all have to work with vibrations. Even if you're building something that doesn't accelerate like a bridge, it will vibrate. And so a vibration is a time-dependent phenomena, so it will induce time-dependent stresses. So everyone has to deal with rate dependence when it comes to stress and strain. So let's take a little look at how a couple of different materials might react in terms of their stresses and strains with how quickly we load it. So we're going to start over here on the left. So we have a graph of stress versus time. So, we'll assume that, we got a couple of little bars of material. They're the same cross-section area. In one case, as time goes by, we maybe hang a bunch of weights on it, and we increase the number of weights we hang on it, somewhat slowly. And then after a period of time, we don't add any more weights. So stress increases up to a certain point with time, because we're maybe adding weights at a constant rate, and then no more. In this other case, maybe we're adding the weights two at a time. Or so basically we're increasing the stress more quickly, a faster rate of stress increase. So we have a high rate of stress increase in case one and low in case two. This is the strain response we might expect. So the strain versus time in our second case, it's not going to change as much. It's going to follow the applied stress response. So we're going to get a lot of deformation quickly in case one because we're giving it a lot of stress, especially down here where stress and strain are linear. And on that subject, if we were to, say, take this case one, where we're increasing the stress a little more quickly, say we were to normalize on time and we were to just plot stress and strain versus one another. So we're going to plot stress as a function of strain. So, for a given deformation, we can go back to our original length at any given infinitesimal point, like we learned about strain, and we're going to look at what is the resulting stress the material is going to pull back with. If we stretch a material such that we've induced a certain amount of strain, how hard does the material pull back? That's one way of thinking of stress as a result of strain. Typically, we think about applying a stress because we think about applying a load to something with a given cross-section area, and then it stretches or it compresses. But we can also stretch a material, so we induce a certain amount of strain and then see how hard it pulls back against us or pushes back if we try to compress it. So either way, we can apply either one, but let's just look at strain as being our independent variable. As we apply small amounts of strain up to about this point, you'll notice that the stress-strain relationship is linear. So we could say that stress on the y-axis is going to be equal to some constant times strain, and let's call that constant E. You guys probably already know this. This is what's known as elastic behavior for axial stresses and strains. And this E, this constant of proportionality, constant between stress and strain, is our modulus, modulus of elasticity. So it's the ratio between stress and strain. I'm not going to be able to write that. So that is the elastic modulus. And so this linear area on the stress versus strain curve is known as the elastic area. And this curve actually is stretched out a bit. For most engineering materials, at least most metals, this is very small compared to the other portion where stress is not proportional to strain. Now, something really important happens here that we'll discuss more. This point where the stress versus strain curve kind of heels over, and we get a lot less stress for every additional increment of enforced strain in the material. This is known as the yield point. And this is where the actual microstructural mechanism of deformation really changes. In the elastic region, where stress and strain are proportional, most of our deformation is resulting from the atoms and crystal lattices or polymer chains just stretching along the lines of their chemical bonds. With polymer chains, we might get a little uncoiling. If you're familiar with polymer chemistry, most thermoplastics at least are coiled chains, coiled around their bond axes. They can rotate. They'll uncoil a little like a spring being basically twisted open a bit. In the case of metals, which are crystalline, the atoms will actually move a little off of their low energy ideal points in the crystal lattice. So they don't like that, so they want to pull back, and hence that's the mechanism by which that elastic stress response occurs. When you pull the atoms away from where they want to be, they want to go back to their low energy positions, and that's really the origin of modulus. Okay. In both cases, the minute you let go of the material, it goes right back to the way it was before. All of the deformation is recoverable. The stress goes back to zero. If you deform the material past this yield point, or if you apply more stress than would correspond to stress yield, then you actually start invoking new mechanisms of deformation. You'll actually move atoms to a new stable position. This is known as a mechanism called dislocation movement in metals, microfracture advancement in ceramics, chain slippage in thermoplastics. But in any case, it's moved, it's in a new stable position, and if you let go of the material, it's not going to go back to the way it was. It is permanently deformed. That permanent deformation is what is known as plasticity, and it's how we're able to form things. So it's a good thing if we're in manufacturing and we're trying to form something and turn it into a new shape. If we are designing a structure to be used in service, typically we don't want that to happen. So as engineers, almost all of our design is going to go on in this realm, in the elastic regime, because we don't like things yielding and permanently changing their shape and surface. That can lead to bad things happening. Ultimately, can be the prelude to failure. So two big portions of this stress strain curve: elastic and plastic. We'll call that P, plastic. Okay. So let's look again at a little bit at path dependence and how this matters. So again, we'll assume we did some kind of tensile test, so we have stress versus time, and we've got a sample here, and we're pulling on it. I'm applying stress, more stress. I'm pulling on my pencil as if it's a tensile specimen. So I pull and I apply more and more stress, and then I leave it at that stress for some time, and then I decrease the stress to a lower level, and I leave it. And just leave it there. Then I do another test where I ramp up the stress to that sigma 2, that stress that I ended on, but I never go up to the higher stress. I just stay at the lower stress, and I never go past that. If we were to plot both of these pathways on a stress strain curve, we would find that in the case of our first test, we would trace this path. We would, go through our elastic regime. But if we yielded, we'd go through point B, we'd go all the way to point A, corresponding to our high stress, our sigma 1 up here, and then we'd back off to sigma 2, and when we backed the stress off, we would follow a straight line that's parallel to our elastic path back here. So the minute we let go of a material, the first thing that happens is we recover the elastic strain. because the material wants to give that back first. It's thermodynamically, it's energetically most happy in its little stable position. And even if it slipped, it's still being stretched. So it'll recover that elastic stretch and go back, in this case, to point A. So if we were to measure the resultant strain, we'd get strain 1 in that case. If we look at our second test, where we never went to that high stress, we go to point B. So we go from 0 stress, we increase it to sigma 2. And we don't go any farther. We just sit there at sigma 2. We'll have strain 2. So if we're talking about a tensile test, in the case of test 1, I'm pulling on my pencil. When I pull it really hard to sigma 2, then I relax it to sigma, or to really hard to sigma 1, I relax it to sigma 2, it's going to have elongated a certain amount corresponding to strain 1. I do it again, and I pull it just to sigma 2, not nearly as hard, and leave it. My pencil will be not as long in test 2 as it was in test 1. And a lot of that is because this portion of strain is plastic. I've already yielded. So as I come back, I'm only recovering. As I drop the stress back down, I end up only recovering the elastic strain. So this is an example of a path-dependent behavior. We weren't all elastic. If we'd been path-dependent, it wouldn't have mattered where we'd gone. We could have gone to sigma 1, sigma 2, sigma 3. As long as we ended with sigma 2, if we'd gone right to sigma 2 in the first place, we would have had the same strain if it had been path-independent. And had we stayed down in the elastic range here, where that stress-strain relationship is linear, that's what would have happened. The very fact that we ended on the same stress, but we didn't have the same strain, and presumably we were conducting the test at the same temperature, we yielded. We weren't elastic. We got some plastic deformation in there. And the difference between strain 2 and strain 1 is the permanent deformation. We could have let go of the pencil, and the difference in length would be that. So, which of course brings us to plastic versus elastic behavior, which we've kind of been talking about. So these graphs make it a little more clear. We'll blow them up a little bit just to see them a little bit more clearly. So just characteristics of elastic behavior. The elastic strain is recoverable. Stress and strain are proportional, so makes a straight line, and it is a straight line through the origin, because you don't start with any strain and you don't start with any stress. I mean, it's presumed that you have a specimen and it's its known length. Here's my test specimen. It is not under any stress, and it is its original length. So delta L is 0. L0 is L0. So strain is 0. So it's not just a straight line. It's a straight line through the origin. And most importantly, it applies at really, really small values. So in fact, one definition of yield is what's known as the 0.2% offset yield, and that's actually being shown here in this little figure. So you notice that we don't have a straight break. Like there's not a little square edge or something here showing that, oh, we've now started to yield. It's kind of a gentle curve that kind of heals over, and in fact in some materials it's really kind of hard to tell when we've gone from this proportional stress strain elastic regime to a non-proportional area where we know we've had some yielding. So one way to kind of take care of that ambiguity in measurement is to define a yield that gives you a little wiggle room for where exactly have we started to yield, and that rule says you basically assume 0.2% permanent deformation. So your yield stress is called the 0.2% offset yield. So you define that as the stress that corresponds to the point here where if you increase the stress in the material, it yields plastically just a little bit, such that when you release the stress, you let go of it, and you trace back a line parallel to your modulus, basically, which the material will retract. In this case, if we're pulling on it, you recover all the elastic strain, you end up with permanent deformation equal to E0 here, strain 0. That strain is 0.2%. So you basically define the yield point not at the exact point where stress and strain are no longer proportional. You say we're gonna allow 0.2% plasticity, 0.2% strain that is non-recoverable, and that's known as the 0.2% offset yield. And it's called offset because you find it by plotting your stress strain curve and then remembering to take this point and draw an offset to your elasticity line. These two are supposed to be parallel. You do not drop it straight down. That would give you a much too large of a value for strain, and you would call the stress too small. It has to follow a line proportional to the modulus, which is how the material would unload. It would recover that elastic strain first. Okay, so 0.2%, that's not a lot. So that's the whole limit of your elastic behavior. By contrast, ductile materials will experience a strain in this regime, the plastic regime, of several tens of percent, sometimes 100% for a very, very ductile material. So 0.2% versus 50%. So the elastic regime is tiny. And in fact, when you see some of these stress strain plots for engineered materials, that you won't even see the elastic regime. It'll be, it'll look something more like that. And then failure is usually denoted by a little X at the end. Okay. We will not be dealing with plastic behavior. We will deal with onset of yield and how to predict when we are likely to get yield based on our elastic properties and a yield criteria that's based on test data like this. But we can say some things about plastic behavior to keep in mind for design. It's non-recoverable, great for forming, bad for in-service applications. Stress and strain are some function of another. I shouldn't say necessarily they're not functions of one another. We generally don't know what they are. We'll find that function more or less empirically. There's some power law functions. They're certainly not linear functions of one another, generally speaking. And it applies for larger stresses and strains. So I should say they're not linear. I'll put a general note about this. It's very rare for there to be a very linear relationship in the plastic regime. And much larger, unless we have a brittle material where we're not really going to get a lot of plasticity anyway. Again, we're talking orders of magnitude difference in terms of how much strain we're going to have, plastic versus elastic. Okay. Again, we won't concern ourselves so much with this, but the area right around yield, you'll see yield associated stresses with different names, the proportional limit, the elastic limit, and the 2% offset yield. They all have slightly different definitions. So the biggest reason that we're presenting this here is so when you look something up in a handbook, you have an idea of what it's talking about. Proportional limit stress is when you stop having a proportional relationship between stress and strain. So it tends to be the lowest stress associated with yielding phenomena. The elastic limit is the highest stress, which gives no detectable plastic strain, which of course depends on the detection method, the detection limit of your measurement method. So that's going to be real consistent, from one test to another, which of course is why typically the values that are reported are that 2% offset, because that kind of normalizes everybody else's test methods. Just about everybody can measure that. Okay, so we've got a reasonable idea of yield, plastic behavior, elastic behavior. So what about fracture? We're generally going to design down in the elastic regime where we're not even going to have to worry about yield, but there are some materials for which yield and ultimate strength, in other words, ultimate being the strength at which it's going to break, are pretty close. So our very, very strong materials tend to be brittle, which means they'll behave elastically right up until the point that they break. So for that, we'll look at, again, tested empirical values for ultimate strength, and this will typically be ultimate strength in tension, which tends to be the lowest. Materials, a general rule of thumb is materials hold in compression, they break in tension, they yield in shear. And that second one is one that we'll base a method, a yield criteria method on, that we'll get to after we look at stresses and strains at different orientations within a material. But if we put something in tension, especially in bending, the tensile side of a bending sample, we tend to open cracks, and they'll propagate more easily than we can get all of the deformation mechanisms going. So when you're looking at material values, if you see ultimate strength or material strength, sometimes you'll see a sigma UTS, and that means ultimate tensile strength. And that's this point on the stress strain curve where it broke. And you will still at that point recover the elastic strain. So if you went and measured the broken sample and went to see what length it was, you wouldn't measure, effectively that strain. You'd measure this one. But if we've had a long plasticity regime, then this difference is negligible. So typically, the strain at failure will be measured right off the stress strain curve. Strain at failure is also known as ductility, if you see that in a handbook. Another concept that we'll touch on later on in our discussion of Hooke's law is something called elastic strain energy. Something that you'll notice if you plot units. If you look at the area under this stress strain curve, you'll notice that it has units of stress because strain is dimensionless. If you look at the units of energy per unit volume, you'll notice it has the same units as stress, which has the same units as the area under the stress strain curve. And that's a good way to remind yourself that the area under this curve is literally the energy required to either strain something and keep it in that stretched configuration, compressed, stretched, twisted elastically, or the energy necessary to make a yield and plastically deform it. So we'll be calculating, as it turns out, when we look at strain energy calculations, which we'll use our stress strain relationships to get, we'll calculate the energy under this portion of the curve. So we'll calculate strain energy, which is the total energy necessary to elastically deform something to a certain point. And in this case, it was just with a uniaxial tension kind of deformation, but that's another elastic property, elastic strain energy. And for those of you who are going on further in the field of material science or failure, this elastic strain energy is the driver of crack propagation, as it turns out. You'll have some of this strain energy at the tip of a crack, and releasing that is the energetic drive for crack propagation. So it's not always your friend. Okay. Let's see, we've covered this. Modulus, elastic modulus, big elastic property. We're going to see this a lot. It's the foundation for Hooke's law, along with Poisson's ratio, which we'll get to next. And remember that it's the line, it's the slope we follow as we load a material and unload it. So anytime we start to load a material, we start to unload it, we instill or release that stretch elastically. Two ways to design. What we'll mostly be doing, elastic design says design such that we are well below yield, and we'll be using safety factors. So, if a material yields at 100 psi, typically we'll design such that it never sees more than 50, and we have a 2x safety factor. And that takes care of the fact that we are never quite sure exactly if the piece of material that we are buying and designing with will in fact have the rated strength. Typically manufacturers sell according to what's average. Woe betide the person who gets the thing that's 3 sigma to the weekend. Your roof's going to break. So we use safety factors to allow for the fact that materials are not consistent, and we can't test 100% or we would have nothing to sell. Furthermore, customers and users of our designs do not always use them in the way we say. This is why what are known as live loads that we can't control, what somebody puts in a building as opposed to the weight of the building itself, for instance, have higher safety factors. So we don't know what somebody's going to do. We're not there to tell them, "No, don't put that there, that's too heavy." So we use a bigger safety factor. Ultimate design limits stresses to avoid fracture. So that would be the case where either yield was not a problem, it's okay to let something yield. I can't think of particularly any designs where that would be the case. This would also apply to cases where the material is going to fracture before it yields. So more brittle materials or ones that have enough inherent flaws that failure by fracture is likely. Composites unfortunately suffer from that. So you might be doing an ultimate design if you're designing a composite material simply because it might be fracture prone. Okay, not that composites are the only materials that are fracture prone. There are some metals, but composites definitely have that as a challenge. They also have a great strength to weight ratio, so it is all a trade-off. Okay, speaking of composites, homogeneity and isotropy. If a material has the same mechanical properties regardless of what spot physical location in the material you look, so like if you machine some tensile samples out of this material in all these different places and they were all aligned the same direction and you pulled them and they all gave you about the same break strength, the same yield strength, you'd say the material is homogeneous. It doesn't vary. So a big piece of metal is very likely to be homogeneous. A composite, absolutely not. The fibrous reinforcement is going to have a strength and more importantly a modulus, maybe orders of magnitude more than the matrix. Okay. Generally in our course we're going to assume that everything is homogeneous unless otherwise stated. So we're going to be looking at things on what's known as a continuum basis. So that means we basically take all the crazy mechanisms that contribute to a material's elastic properties and yield properties and treat all of those as a single number. The modulus, the Poisson's ratio, the yield strength. We're not really going to care what it took to get it there. If you go on and take Intro to Material Science, you'll get into all the chemistry and microstructure that it took to achieve that one number, but we're just going to use the number. But that number will change depending on how the material was formed and processed and what its chemistry is. Something that is more likely to be encountered, so homogeneity is something that's generally desired. You will generally only encounter non-homogeneous materials if, like I said, it was designed to be non-homogeneous or it's defective. So homogeneity is something that's used as like a quality test. Isotropy means are the materials the same in different directions? So if you look at like tensile test sample number 1, it's like a little dumbbell. It's pointed aligned with the y-axis, and tensile sample 3 is aligned with the x-axis. So if we tested these two samples and we did a statistically significant sampling such that, we could really say, all the samples we take that are aligned in the y direction maybe have, a yield strength that's 50 KSI on the average, and the ones aligned with X are 200 KSI on the average. This would be a non-isotropic material. We'd say that it has properties that vary with orientation, and sometimes that's a good thing. Sometimes we want all the strength or all the modulus, high modulus in a given direction, and really don't want it in another. So continuous fiber composites are kind of the ultimate example of a non-isotropic material. When we start to look at Hooke's law, and we make a big matrix out of our stress-strain relationship, and we look at stress versus strain in the XX direction, the YY direction, the XY direction, etc., kind of like we did for stress and strain individually, we'll start to build a whole matrix of elastic properties relating stress and strain. And for isotropic materials, we'll be able to describe all of the elastic properties with like 3 values that are related themselves. For non-isotropic materials, we need an entire matrix because, for instance, elastic modulus could be different in the X direction, Y direction, Z direction. All the other elastic constants could be different in all the different directions. So non-isotropic materials are more complicated for modeling and for designing, but they can give you properties and they can give you an advantage in design that an isotropic material can't. Very few uses for non-homogeneous materials. They're probably out there. Okay, so we've covered that. You can read this over, and I'm sure this is covered in depth in every textbook. Okay, so we've covered elastic tensile modulus E, which is the relationship between normal stress and normal strain. So it's also known as Young's modulus with a capital Y. That's a person's name. The next elastic property that we'll get to is the relationship between strain in the axial direction that we would apply stress to and the direction perpendicular to it, radial or diametrical. So if we've got a cylinder, for instance, and we've got the y-axis pointed in the axis of the cylinder, and we apply a stress to it. If it's a tensile stress, we know it's going to elongate, and it's going to elongate to have a strain that's proportional to the stress by the elastic modulus. Well, as it turns out, it's also going to get skinnier. And the ratio of the strain in this radial direction, so here's our axial direction. This is our radial direction, Z and X, and I can't draw straight, and I apologize. Let me erase that a little bit. It's already drawn here. Is what's known as Poisson's ratio, and that's another gentleman's name, I believe. So Poisson's ratio is, as it turns out, has to be less than 1/2. It's we end up with a negative sign indicating that if we stretch in the axial direction, we compress in the radial and vice versa. So if I had applied a compressive stress and ended up with compressive strains in the axial direction, the cylinder would get fatter by Poisson's ratio in the radial direction. So, and this is strain in any single radial direction. So that would be, if this is EYY, this would be EZZ or EXX, which if it's a cylinder and it's isotropic are going to be the same. So as it turns out, if Poisson's ratio is 1/2, that corresponds to the behavior of a fluid. And we'll find that if you look as you do exercises and you look up in a handbook of material properties, or you're given material properties to use to do some problems, you'll find that a lot of rubbers and other elastomeric materials. This is not to be confused with elastic as in the elastic range where stress and strain are proportional, but elastomers, like polymers, rubbers. They tend to have Poisson's ratios close to 0.5, and fluids all do, and elastomers tend to behave quite a bit like fluids. Incompressible materials will have a Poisson's ratio of 1/2. So that's just something to keep in the back of your head. If you're doing some calcs and you get a Poisson's ratio of like 2, check to make sure you didn't maybe have something backwards in your calculations. So we've covered a lot of material properties in this lecture. It turned out to unfortunately not be as short as I had planned. A lot of exciting things about materials. Qualitatively, we've covered elastic versus plastic behavior, yield stress as the dividing line between our recoverable proportional elastic behavior with very small strains and our plastic behavior, permanent deformation, usually large strains, higher stresses generally speaking, non-proportional behavior. We've looked at ultimate behavior as being where things break, elastic design where we apply appropriate design stresses and safety factors such that things don't yield, and ultimate design where we do the same thing such that they don't fracture. And we've defined 2 elastic constants. One, the tensile modulus, Young's modulus, which gives us the proportional constant between stress and strain for normal or axial stresses and strains. And we've defined Poisson's ratio, which relates strain in the axial direction to strain perpendicular to that axial direction or diametrical radial direction. So in the next lecture, we're gonna do a little bit of mathematics, and we're going to look at how stress, strain, elastic modulus, and Poisson's ratio all work together to allow us to calculate stress and strain in materials with different loading and ultimately at different orientations with respect to the loading directions. So stay tuned.